Hi, good morning, good afternoon, or good evening, depending on where you are. I can see the numbers signing in. It's clicking up rapidly. So I'm going to wait just a minute so that people don't miss the start. So I'll start in about a minute. Okay, so there's still a few people joining, but I'm going to start now with a few just introductory words, and hopefully we'll have a few more people by the time I've finished. So welcome to this last webinar of the year on undertaking cable failure investigations, and I'm going to cover some general basics of forensics and also then a specific case study. We'll have a Q&A at the end of the session. So in the little panel on your right-hand side, you should see a tab labeled questions. If you click on that, it'll open a dialog box and you can type any questions in there. And depending on how much time we have at the end, I will try to answer some of those. If the box is a little on the small side, there's a little box with an arrow pointing out of it on the extreme right. If you click that little box with the arrow pointing out of it, it'll undock the box. It'll make it bigger. You can drag it around your screen to make it easier to type questions in. Also, at the end of the webinar, before you leave, a survey should pop up with a few questions from our events team asking for feedback, and also importantly for suggestions what you want to hear from us next year. We're in the process of planning the webinar series for next year, and also thinking about ways of trying to change the format a little bit. So with that, without further ado, I am going to turn my camera off, save bandwidth for people. Get started. So welcome to the webinar. My name is Simon Sutton. I'm the International Director for International Services. I'm also one of the lead consultants for cables at Doble. So today, what we're going to be looking at is, I'm going to give some basic introduction to root cause analysis, which applies to anything you want to look at. It's not just cables. You can use this for transformers, circuit breakers, or any other failure investigations you want to do. Some basics. And most of you, common sense, will get you a long way with some of this stuff. We'll look at some of the analytical techniques that you might see coming up in people's reports. We'll look very briefly at what you should expect to see in a report. And I have a nice case study at the end, which actually demonstrates some of these things quite well. So before we delve into the details, for anyone who's not very familiar with Doble, we're a company that's been around for over 100 years now. We formed in 1920 by, surprisingly, Mr. Doble, and we were a family-owned business all the way up till about 2007, when we were acquired by Esco Technologies. And then since then, Doble's been growing, particularly since about 2017. And in that time, we've acquired a number of companies, which has really expanded the technologies and services that we can offer. So if you think you know what Doble used to do, think again, we're quite a different company today. And as an example of that, when I joined in 2017, we were only 300 people. And as you can see here now today, we're over 800 globally. So we've grown a lot through acquisition and all those brands across the bottom of the screen. are now all part of the Doble family of companies, and we operate around the globe. And I can see from the attendee list that we have people from all around the world, either registered or online now. One important thing to say is you will all get a recording to this automatically, and those who have registered but aren't actually online with us at the moment will also get that recording. So if there's ever a webinar, a Doble webinar you want to attend in the future, and you think you won't be available to watch it or listen to it live, register, and then you will get a link sent to you afterwards with the recording. And within Doble, basically we have three sort of pillars of our business. We have the testing equipment, so that's instruments for testing, high voltage equipment, medium voltage equipment, on-site generators as well. We have monitoring systems, so pretty much these days, if it's inside the boundary of a substation, we have online monitoring equipment for it. And then we have professional services, which includes things like helping people procure, so reviewing specifications, factory witnessing inspections, manufacturing inspections, FATs, asset management support, failure investigations come into this area as well, and also things like training and the events we run. So within services, as I say, online, offline testing, we have test teams in different countries, consulting, witnessing, commissioning in certain places as well, and forensics. So with forensics, the key here really is, we really want to know, why did it fail? Why did it go bang? Why is it now a pile of black pieces? And to the last point there, failure investigations are often like a jigsaw puzzle. As we do the investigation, we slowly start to put the pieces together. The problem is often with the energy of the fault, then we often lose some of that evidence. We don't have the whole picture. So we're often trying to end up with the most probable cause rather than 100% this was the problem. There's a number of sort of recognized standard methodologies for doing root cause analysis. There is an IEC document that covers failure investigations. It's not a great document. It generally lists a lot of the standard methodologies, has a brief description of them, but doesn't really give you any good information on which approach to use in which instance. These are all tools. There's no one right or wrong way to do a failure investigation. Some of these approaches are better than others in certain circumstances, and don't think that if you've been taught one of these, it's the only way to do it, and I'll come back to that later. And I'm going to give a couple of examples of a few of these in a minute. So the 5 whys analysis is quite a common one. You might have heard of this one before. It's pretty simple. So you define the problem and you think like a 3-year-old. So anybody who's got kids of a certain age will know that every time you give them an explanation, they're immediately going to ask why. So in this instance, with the little cartoon here, so it's why did the machine stop? Well, it tripped out. Why did it trip out? There wasn't enough oil on the shaft. Why wasn't there enough oil? Well, the pump was inefficient. Why was the pump inefficient? Well, the pump drive shaft was worn. Why was the drive shaft worn? Well, the oil filter was blocked. Now, you could then ask again, why was the oil filter blocked? And the answer probably is the maintenance wasn't done as it should have been. And quite often in our industry, we come back to issues to do with either the wrong maintenance being done, not being done often enough, or done incorrectly. But just keep asking why, and drill your way down. So it can be the 6 whys analysis, it can be the 7 whys analysis, but you keep drilling down using that technique. And don't accept the first answer. You keep going until you get to the problem. Another simple example, again, probably familiar to people. Why won't my car start? well, the battery's dead. Why is the battery dead? Well, the alternator that charges the battery isn't functioning. Why is the alternator, why isn't it functioning? Well, the belt is broken. Why is the belt broken? Well, it was beyond its useful service life and hadn't been replaced. So again, we're ending up with a maintenance issue, and so we didn't follow the recommended service schedule for the car. So again, you could just stop with the battery is dead. Well, okay, I get a new battery. If I put a new battery in, we're going to end up with another dead battery because we haven't actually got to the root cause, which is the battery wasn't charging. Ishikawa diagrams, named after Mr. Ishikawa from Japan, also called fishbone diagrams because it's meant to look like the spine and the ribs of a fish. These are kind of a glorified brainstorming mind map kind of session diagram. So it's a way of capturing lots of information, but without necessarily telling you what's important. They're quite useful if you want to brainstorm with a colleague, to make sure you haven't overlooked something. So you can create a diagram a bit like this, and then share it with colleagues. You can email it to somebody and ask for their input as to whether they can think of anything that you've clearly missed. You should get a set of these slides afterwards, so don't worry about reading how to make a bad cup of coffee. It's a trivial example, and you can find these diagrams, on the internet. And there's a whole bunch of standard templates, and because of course these days everything has to alliterate. So we've got the four M's for manufacturing, the 6 P's for processes, the 5 S's for services. They're useful, and as I would say, use them as a way of trying to think of things that you haven't overlooked. But as I say, it doesn't really give you any information about what is more likely than something else, or is it really important in a particular case. So those are the only 2 I'm going to use. As I say, there are other methodologies out there and other approaches for doing it. What I would say is don't become handcuffed or shackled to any one approach. I've had a number of clients over the years who, when we've submitted reports, have come back and said, no, please rewrite the report because you haven't written it in the 5 whys analysis approach. Or I need to have an Ishikawa diagram for my management. And it's clearly because they've been on a training course, they've been taught one methodology, and for them, that's the only way that they have been taught, and therefore they think that's the only way that you can do something. So remember, these are tools, and you pull out the appropriate tool from your toolkit as and when you need it. So don't get hung up on any one of them. So if I do this as an interactive session in a classroom with people, I normally say to them, okay, what would you do now if your manager walked into the room and told you that there'd been a failure somewhere and you need to go to site and start the root cause analysis? And usually people talk about, well, they're going to pick up various bits of test equipment and they're going to go out and start the repair. And obviously, number one, when you get to site, please make sure that the area is safe. If it's a cable, particularly an XLP cable, there could be a lot of stored charge in there. So please make sure everything is earthed down safely before you do anything. If it's an oil-filled asset, think about safety, think about slipping, think about the fact that it may have PCB if it's a very old asset in it. But please make sure everything is safe before you do anything. The other comments on this page, and most of you will probably intuitively know these things because you have watched murder mystery programs on the TV or programs like CSI. And when they walk into the room and there is a dead body on the floor, the first thing they do is not start moving the body around. The first thing they do is they label things, they take photos, so they know exactly what is there before they start. Once you've moved it, you've potentially destroyed evidence. Photos are fantastic, but we all carry a video camera around with us in our pocket these days on our phone. Video can also sometimes be much more helpful. You know, a photo is two-dimensional. It's really hard to judge what something looks like in 3 dimensions from a photo. But if you record a video, your brain is very good at putting that image back together to get a sense of shape and scale and how things are orientated to each other. So yeah, take videos, that's really helpful. Put labels on things, take notes, draw sketches. Also scale markers are really helpful. And if you don't have a ruler or a tape measure that you can put into a picture, you'll pick something, a biro, a pen. You know, they're all roughly the same size anywhere in the world, so it gives an approximate sense of scale. Put your hand in the picture, or your shoe or your boot, again, just to give a sense of scale. And if it's something where, take a bushing failure, where things are going to be possibly exploded over a large area, draw sketches, map out where the pieces have ended up, and take copious notes, because once you've moved it, you won't remember. You'll think you'll remember, but by the following day, after you've had 10 other conversations about failure, you'll have forgotten certain details. So photos and notes, really, really important. For cables in particular, because they're long, thin, cylindrical, you know, and are symmetric, if you're going to cut the cable out, and you know, the picture here on the pointer. So, you know, in this case, the cable here is faulted. You can see the debris on the floor here. Now, in this case, it was obvious to know which way up the cable was, because, you know, I can see that the debris is at the bottom. I know the fault was at the bottom, but in many cases, you don't know that. I don't have a photo. So mark the top of the cables, either by wrapping some tape around it, like over here, you know, wrap some tape around it, put a mark on the top, right bottom, label the orientation too. You know, which end is substation A, which end is substation B, or the transformer, or the switch gear. It might not be relevant to the investigation, but if you don't write it down, we will never know. Trying to move something on my screen. So yeah, even potentially put a mark on the insulation. The insulation shouldn't move inside the metallic sheet, but I've seen examples where the cable core is actually quite loose. So again, just put a mark on the insulation such that it lines up with the mark on the top of the cable, or the bottom, or however you're going to label it. Before we start to cut things up, again, it's important to label the pieces as we take them apart. Now, okay, here it's 4 and 4 prime, 8 and 8 prime. It could be A and A prime, A, B. It doesn't really matter how you label it, but label it in such a way that you can put it back together again. And as an example, I was involved in an investigation some years ago, and actually the investigation was conducted by the cable maker. And we were at their factory, and we were there all day. And they were cutting the piece of cable up, and we were taking measurements and examining it. And it got to the end of the day, and it was all laid out on the tabletop. And we went home to come back the following day. And when we came back, all the pieces were missing. And the cable company claimed that the cleaner had moved the pieces overnight, but the upshot of it didn't really matter who had moved them. All the pieces had ended up in a skip of hundreds of identical looking pieces of cable. And because nothing was labeled, we didn't know which bits belonged to our investigations and which bits were just other bits of scrap. So at that point, the whole investigation finished. Whereas if the things had been labeled, at least then we would have been able to recover them and carry on. So the next couple of slides really just talk about a few of the techniques that you're often likely to see mentioned in reports. Some of them you have available to you as you sit listening to me talking about this. Number one, common sense. Does the thing in front of you match the specification? It should do. It doesn't always. And then you also have other things. You have your hands, your smell, touch. If something's had a flashover, often just taking that object and twisting it and tilting it in the light and letting the light reflect off it in different ways will let you see that tracking across the surface. You don't need anything more sophisticated. Actually, sometimes that's far more effective than actually trying to put it under a microscope to see the damage. Smell, touch, all of them are useful. If we want to look at the object, we have all sorts of different types of microscopy. We can take pictures with our phone and blow them up. We can use more sophisticated microscopes to take better photos at higher magnifications. We're often going to see scanning electron microscopes used for looking at things in very, very small objects or particles, and also X-rays, X-ray imaging of items. And in the case study at the end, you're going to see optical microscopy, scanning electron microscopy, and X-ray imaging all in that one case study. If we have unknown material, if we have metallic material, then we're most likely to be using things like elemental analysis, usually performed in an electron microscope. Really good for metals, really good for inorganic material. We can also do things like elemental mapping to tell where certain elements are. If somebody gives you an image from an electron microscope and tells you that a particular material is, and a classic example is, oh, it's copper sulfide from corrosive sulfur problems in a transformer, you can't tell that using an electron microscope. You can tell there is copper there, and you can tell there is sulfur there, and provided the sample is fairly flat, you can get a good estimation of the ratio of copper to sulfur, but you can't tell it's copper sulfide. You need a chemical test for that. So elemental analysis will only tell you the elements and their approximate percentages. We also have an X-ray technique called XRF, again, good for metallic materials. It can be portable. There are portable units, look a bit like a large handgun that you can take to site. It's also very good for particles in oil, if you don't want to have to try and filter them out of the oil. If it's organic material, oils, greases, plastics, then we're going to probably be using some form of spectroscopy. Infrared is the usual one, but it could be UV vis or near infrared. And for FTIR, there are huge libraries of spectra out there. So sometimes you can actually not only identify the material, but because of the additives in certain things, you can even be able to get the brand or the source material as well, where it exactly came from. And then lastly, and I've seen this in certain investigations where you may actually need to go back and repeat some of the tests that were done at the factory. Some of the tests which are laid out in IEC or IEEE documents. And if it's a cable, that can be just simple things like checking the dimensions of the cable, checking the thickness of the layers, the concentricity, etc. So before we move into the case study, I just want to talk a little bit as well about forensic reports. Obviously, I write them. as part of my job from time to time. But I also sometimes see reports from other organizations where either a client has got 2 or 3 conflicting reports and they don't know how to interpret the evidence, or they're in dispute with maybe the supplier of the equipment, whether that's a bushing or a cable or whatever. But we do from time to time see reports. So I like to think I know what makes a good report, or conversely, what makes a bad report. So I would always say that you should have a clear description of what happened, where and when at the start. If only for the fact that if you put that report in a filing cabinet or on a hard drive for 10 years, and then somebody comes back and looks at it, they have a summary of everything that happened. Likewise, all the documents that were shared as part of the investigation. So you have a snapshot in time of everything that fed into why was that investigation going on and what was the basis and where did they start from. Likewise, good photos, all the various photos you'll see in a minute in the report are generally as they would appear in the report. I tend to do all my photos in PowerPoint, so I can put arrows and circles on, annotate things, and then they get cut and pasted straight into the Word document. So hopefully, when it says figure 3 shows, it's very obvious what in figure 3 I'm talking about, because there's an arrow pointing at it, or it's circled. What testing did we do? What did it reveal? And ultimately, at the end, a discussion bringing all the evidence together, and then some form of conclusion. Now, as I said at the beginning, often these failures destroy a lot of the evidence. So we're not necessarily always going to find that smoking gun of what killed the cable or the transformer or the bushing. So the conclusions of the report may be somewhat nuanced. It could be that it's highly likely it's A, unlikely that it's B, but B is still possible. So we need to be careful with the language we use, but again, trying to give people an indication of what the root cause was. And if you don't know, I think it's fair to say that there are cases where you get through all the evidence that you have left, and you can't actually work out what the root cause was. So I'm going to give a case study from a few years ago. I think this one's quite nice. It's a medium voltage cable investigation, but it shows a number of the techniques and a number of the analytical techniques. We use the 5 whys in this one, and it also shows the risk of being shackled to some of these techniques. So in this case, it's a 3-core cable, 34.5 kV. Only been in service for 4 years. They put in 2 circuits at the same time at a petrochemical facility, and they'd had 2 joint failures within about 3 or 4 months, and they had another one during the course of the investigation. So clearly they were very worried about, were they going to have more failures? What was the problem? Because in their context, if the circuit went out, they lost production. That was big money to them. They sent me 2 lengths of cable, each containing a 3-core joint. So they sent one with a fault in it, and 1 healthy set of joints for comparison. And as compared to utility customers, industrial customers are not necessarily the best at keeping records. So although these cables are only 4 years old, they had no details on the cable design or any drawings for the joints or cables. So I didn't know where I was starting. So obviously I can see what the cable looks like because I have a cut cable end. So it's 3-core cable. We've got a lead sheath. There's a PE jacket over that, and then also armor wires over that. These are land cables, but certainly in the Middle East, it's quite common for land cables to be armored. So it's a three-phase joint. I appreciate that we may have people on the call who are not out and out cable experts. So let's get my pointer again. Oops. So normally when we're constructing the joint, we have 3-core cable on either side. We break out the cores, 1, 2, 3, and then we join the conductor, and then the joint body gets applied over the top of that. So we have 1, 2, 3 joints. Then there's going to be some kind of mesh sleeve that contains all the joints, and then a thicker earth continuity braid for carrying fault current from one side of the joint to the other. And in this case, there's a metal canister and then an outer sleeve. So there's some kind of containment to keep water out as well. But obviously, from the forensics point of view, we're going in the opposite direction. We're starting on the outside and working our way in. So everything is upside down. So we're starting from the outside and we're trying to break our way in to get to these 3 joints. So we had the 2 cables. We had no information. So the sensible thing to do was to start with the healthy cable and break our way into that one to discover what was inside. The logic being, well, actually, if we caused any damage in getting into those cables, into those joints, it didn't make any difference because we still then had the faulty cable. We would learn from the first one. We could then apply that to the faulty cable afterwards. And we'll see in the photo here. So these are a little bit complicated for the screen, but so here's one of the jackets, so there's a polyethylene jacket. We can see the armor wires here. There's a band to stop all the armor wires splaying apart. You can see the lead sheath, and then we have the 3 cores in the bottom left-hand corner over here. Once we could actually open that up a little bit more, here's the earth continuity braid, the thicker braid, and we can also see the wire mesh bag. Remember these bits because they're important later on in the analysis. So first thing, so once we got the 3 joints out, here they are. You'll see that I have labeled both ends. We didn't know, number one, we didn't know which way was up and which way was down on those particular cables. So we arbitrarily labeled it based on the way that it arrived in the crate. And again, we just labeled it end A and end B because we didn't know anything else. And phase 1, 2, and 3. But you'll see, everything is labeled. So if I move them, somebody comes in and moves them, we know exactly what we're starting from. We have a scale marker, so this is about 1 meter from end to end. The labels. Now, interestingly, I said we started with the healthy cable. When we took the 3 joints out of the healthy cable, this is what we found. We found the fault path. This is the importance of labeling things carefully. So the client who shipped the samples to me mislabeled the cables. Okay, they had a 50-50 chance of getting the label on the right cable, but they failed that. So we were very lucky. As I said, we started with what we thought was the healthy cable, assuming that if we damaged it, it wouldn't make a difference to the investigation. The reality was we started with the faulty one without knowing it. So you can see the fault path here in the joint body, and obviously there was quite a lot of fault current because not only is it broken down here, it's also ablated part of the surface of the joint that was facing it, like in the little picture over here. So what do we do? Well, we're going to be really systematic. We're going to do a visual inspection and we're going to take lots of photos as we go. We decided to x-ray these joints before we did anything else. Then we were going to undertake the dissection. Then we were going to use optical microscopy to look at the various things we found. And then ultimately we ended up in this case using some scanning electron microscopy and elemental analysis. And we'll work our way through those steps. X-raying is an interesting one. It's maybe not a very common approach, but particularly in some of these cases where I don't know what I'm going to find when I open something up because I have no details of the joints, it can be quite useful. So in this case, you can see in the picture on the right, I'll just put that little picture there. So we're not looking at the full joint, we're just missing the ends in these pictures. So we have the three phases. You can see the conductor in the middle of each phase. You can see the joint connector, or the conductor connector here. This is a crimp style connector. And then on the outside, you can see the joint body. It usually takes a few goes to get the x-rays right, but the company we use isn't that far from our offices in the UK. I can take the samples there. We can do the exposures. If they're not right, that we can do them again immediately. It's all digital these days. It's very quick and easy. You can see that they've labeled them. They've mirrored my labeling. That says F1A, F1B, A and B for the ends, failed for F for failed. Phase 1, this one over here is 3, and obviously 2 is the one in the middle. And we do three photos of each joint, rotated 120 degrees each time, so that we don't get anything which is shielded by the conductor or the conductor connector. It's a little small on here, but this is actually the fault path here in the little green circle, and we'll blow that up in a minute so you can see more. So here's that exactly the same image blown up. This is the resolution on these images is phenomenal. There's no refocusing or doing anything clever. That's exactly the same image, just zoomed in. So we can see the fault path here. And within the fault path, we can see what appears to be some contaminants of some description, some little hairs or something. Now, the advantage of this, knowing that that's there, when I'm going to cut that joint open later, then I know to be careful, that there's material there that I might want to actually keep for part of the analysis. But as we also look into these images, and remember that we have 6 joints in total, 3 from the failed circuit and 3 from the healthy circuit, we can see some other features. These dark areas are air voids. So in an X-ray, black means lower density. So we have some air gaps here. And if I were to blow these areas in here, these are layers of tape over the conductor connector, and we'll see that in an image in a minute. But I can even see that there are air gaps in those layers of tape, between those layers, which are probably only 100, 150 microns thick each tape. But importantly, we also seem to have this other feature here that looks like a developing fault. I can see something starting to penetrate through the body of the joint. By knowing the orientation and knowing where it is, again, when we cut this joint open, we knew where to avoid so that we could actually preserve that feature. So if I'm in a classroom in front of people, it's a lot easier to talk about this by waving my arms around in the air. But I'm going to have to try and do this with pictures. So to open up the joint, basically what we do is we cut down one side along the length, and then we're going to flip it over turn it through 180 degrees and cut on the other side. So 12 o'clock, 6 o'clock, 3 o'clock, 9 o'clock, depending on how you want to look at it. But opposite sides of the joint, cut all the way along the length, and then we can open it out to see what's on the inside. So again, we're going to kind of open it up like this. So all the images we're going to see in a minute is looking on this inner surface of the joint body. So here we go, and here's the opened up joint, the 2 halves of the joint. Here's what's left from the cable inside. We can see the XLP insulation at either end. We can see the tapes over the conductor connector. The conductor connector is under these tapes. So if we look more closely at these tapes, we can see that there are various little spots and brown deposits. Within the course of the investigation, we never actually delved down into exactly what this material was. We could have done, it wasn't actually particularly necessary. But all of this was localized to the ends of the conductor connector in this region where we could see air pockets and presumably partial discharge going on. If we looked at these surfaces in more detail, you can see ablation of the material. So again, clear evidence of kind of partial discharge activity going on in that region. So back to where we were with the little contaminants before in the fault path. Once we actually took the joint body off, these are now the tapes over the conductor connector. We could see that there were little wires embedded in the tapes. Now, the fact they're embedded means they couldn't have fallen in after the fault. You know, they're actually stuck into the layers of tape. Again, the way this is laid out on this slide with these pictures, this is how I would present it in a report to make it very clear where those images are coming from and what I want you to look at. We could sample those wires, and I'm going to show you the electron microscopy in a minute. You know, if there was more than one, there were multiple, and I can only assume that they got stuck into those tapes when the jointer was lapping those tapes on. Either he didn't change his gloves, he didn't wash his hands, but they've ended up in there somehow. But we can actually identify the source of those wires. So here's one of the covered wires. When you look at the surface here, it's covered in like a layer of crust, which is presumably carbon from the fault, from the energy deposited on. But we can still get an elemental analysis, which implies that it's a tinned copper wire, not surprising, and we can measure the diameter. But then we can also do that for the thin wire mesh sleeve bag that goes over all three joints. And we find that it has basically the same elemental composition and the same diameter. And we can also do it for the continuity braid, which also is tinned copper, but although actually it looks a different size, these are 105 microns in diameter. This is 150 microns in diameter. So it's a much thicker wire. It's got to carry up, you know, that braid has to carry all the fault current. So it's a thicker wire, even in the same material. So we can tell that with a high probability that the wires embedded in those tapes come from the mesh bag or the mesh sleeve, which makes a lot of sense. It's very fine, it's very fragile. You can understand why it could potentially break, and you could, the jointer could get those wires onto his hands. So let's think about our 5 whys analysis. You know, why did it fail? Well, it broke down to earth. Why did it break down? Well, there were contaminants in the tape. Why were there contaminants in the tape? Well, they probably came from the hands of the jointer. Why were they on the hands of the jointer in the first place? Well, he probably didn't have good training or good supervision, or both. How did that happen? Why did that happen? Well, that's probably down to poor specification or poor tender documents. It could be that, you know, there was no requirement for, you know, skilled jointers or ones that had gone to a qualified joint school. You know, he could have just been trained on the job. And particularly in the Middle East region, you know, that's entirely believable. So great, you know, we've got to the root cause of our problem. We've found the wires, we've identified where they came from, and we've done our 5 whys, and everything has been successful. This is why you have to be very careful about being shackled to one of these techniques, because you have to think about the other evidence that we have seen. So in those X-ray images earlier, I pointed out the air gaps in there, and also this, what appeared to be another developing fault. These joints that we were looking at are made from silicone rubber, and silicone rubber is really strong when it's compressed, but it's actually very weak in tension, and it's very easy to cause that to tear. So again, when we cut the joints open, we could cut it open so as to not damage this feature. And on the inside of the joint body, we could see, we had a very big crack, tear in that surface, inner surface. We could now cut vertically down through that crack, that chasm. And what we can see is, so outlined here in red, is the extent of the feature. This is a tear surface. It's very smooth. This on the outside here is rough because that's where the knife has gone through. But this is a tear. It's working its way. It's about 70% the way through the body of the joint already. We found tears in lots of the joints. In fact, all of the joints. And if you remember that there were 2 failures before this investigation started, and a 3rd during the course of the investigation. Okay, it is possible that the jointer managed to get wires into more joints, but all 6 joints we looked at that were sent, the good one from the faulty cable and the good cable, all had tears to some extent. So you have to say, why is it happening? Well, the tears are all happening at this end of the cable, where there's a mismatch in the diameter between, or the radius between the XLP insulation and the conductor connector. And you can see that because on the joint here, it's like a dog bone. So the diameter in the middle of the joint is narrower than the diameter out here. You'd expect it to be the other way around. Normally the conductor connector matches the diameter of the insulation near enough, and then there would be a layer of tape supplied over the middle. Now, this is one of the interesting places where when I talk to clients, whereby I say, well, the jointers have used the wrong size conductor connector. It should be a bigger diameter to match the diameter of the cable. And the client took the approach of, no, it always looks like this. It's just that he hasn't applied enough tapes to build up the diameter of the conductor connector to match the diameter of the cable. Now, clearly, the more manual work the jointer does, the more chance there is of him making a mistake or introducing contaminants. So I'm more a believer of it should look like the little picture at the bottom, where the conductor connector is basically the same size as the diameter of the insulation. Then he only has to apply 1 layer of tapes. So the failure in the cable we examined was down to the little wires getting into the tapes. But more worryingly, we found evidence of discharge and tearing in all the joints we looked at, which probably means if they used the same size conductor connector on the entire circuit, every single joint was probably at risk of having failures in the future. And there's not very much the customer can do other than excavate the cable and replace the joints at that point. So that's the end of the little case study. So just to wrap up with the forensics 101 part, what I would say, again, use these standardized approaches with caution. They're useful tools, but don't get tied to any one of them. The more information you can give the investigator at the outset, the better. I often have issues where I start an investigation, we go down one level of, down one route of the root cause, and then the client will miraculously pull a rabbit out of the hat and produce another bunch of documents that they forgot to hand over at the beginning, which then completely changes the landscape and the way that we look at the problem. So it's far better to give everything at the start rather than drip feeding it into the discussion. If you're going to send the samples away to somebody, please make sure everything's very well labeled before you send it. Likewise, take photos, take videos before you start to move things, before things start to be cut up. I listed some analytical techniques. There are lots and lots of others which are going to get used in investigations from time to time. Generally, if you're the person receiving the report, you don't need to understand the science of the analytical technique, but hopefully the report tells you what the results mean, so you can help build that picture and interpret the ultimate findings. And don't always expect a smoking gun, because often that evidence is gone. So with that is all I wanted to say. We've still got about another 10 minutes or so left available, and I'm going to try and have a look to see whether anybody's asked any questions, and they haven't. If anybody does want to ask questions, oh, there is two, hang on. I might pop it out, I can see. So we have two questions that were, oh, now we've got another one. Okay, we'll put you on. So the first couple of questions, I'm going to follow up afterwards because it relates to GIS testing, and I don't quite understand what the question is asking. So Riyadh, I will send you an email afterwards about your questions and follow up with you. So somebody asked, with the case study, the second cable, the second fault that circuit experienced, was it the same as the first? The simple answer is, I don't know. They only sent us that one failed joint with the three. Sorry, the one failed 3-core joint. The other one they'd already repaired, and probably that evidence had been scrapped. Again, one of the hard bits of doing this job as kind of a consultant is you don't always get to find out what happens afterwards as well. So with that particular case study, I made recommendations for what they needed to do. I have no idea whether they did them. So sometimes you can make your suggestions and don't always get to find out whether you were right or not. So we have a question here about predictive methods and testing that we could use to know the health of our cables. That's an interesting one. So it largely depends on the type of cable. So whether it's an XLPE cable or an oil-filled cable. Oil-filled cables, people will do DGA sampling. The interpretation is difficult, and you need to make sure the samples are representative. If it's an XLPE cable, and depending on if you think it could suffer from water treeing, so people will do VLF tan delta to detect for water trees. That's normally for medium voltage cables that don't have a metallic sheath. And then if it does have a metallic sheath, and even if it doesn't, partial discharge testing is probably as good a method as we get these days. Usually because if we think about it, the cables are factory tested, the joints are factory tested before they arrive at site. Most of the problems with cable circuits are either caused during the installation, so it's a defect in the accessory, so partial discharge is very good at picking that up, or it's going to be where somebody digs into the cable and damages it from the outside. In which case, sheath testing, so measuring the resistance between the metallic sheath and earth, and if the jacket of the cable, the oversheath, is damaged, you'll pick that up, and then you can start to find ways of narrowing down where it is to repair it. So somebody's asking me whether we'll do another webinar on fault location for cables. We will add that to the list of potential topics for next year. As I say, when you leave the webinar, or when you try to leave the webinar, a survey will pop up. So any suggestions for things you want to hear next year, please put it in there. Our events team will capture that. And we are in the process. I had a call earlier this week about our webinar series for next year. And to be honest, and also any suggestions, not just for topics, but for different formats or different ways of doing these webinars that you have, or maybe you've seen one of another company presenting and you think, oh, that's a really good format, let us know, because we want to try and keep them informative and valuable for you folks. So good question. How do you prevent jumping too soon to the conclusions? With difficulty, I would say, is the answer. It's very easy to jump to the conclusion based on not enough evidence. There is one, much as I denigrated the IEC document for root cause analysis, it does have one quite nice little picture in it, like a flow diagram. And it contains a number of feedback loops. So it kind of says, collect evidence, collect documentation, start the examination. And then there's also a bit that then says, well, actually, when you start to do the examination, it might, rather than carrying on with more testing, it might drive you to go back to the beginning again and look for other documents or evidence. It's very rare that these investigations are completely linear. It's as you do the investigation and you start to reveal the evidence, it's often about looking at what evidence you have, creating hypotheses, and then either looking for evidence to confirm or exclude certain options. It's rare that you ever get to the point of the smoking gun. This case study is an interesting one because, okay, you've got the wires there, they're going to act as stress enhancement, they're going to lead to discharge. That's a pretty good smoking gun. But it's not the important thing in this investigation because of all the issues with the air voids, the PD, and all the other joints, and the tearing of the silicone rubber. So it's very hard to avoid jumping to conclusions. Insulation resistance tests, can they detect the voids or cracks? No, I think it's going to be the simple answer there. You've weakened the insulation, but you would not detect it. It's a very small localized defect in a very long length of cable, so I don't think you would pick it up. You should. So the question is, Do we see evidence of partial discharge regularly in XLPE joints? The answer is no. A well-made joint should not have any discharge in it. As I said earlier, the cables are factory tested, the joints are factory tested. It's only when they get to site and people have to put them together on site that problems arise. And you can understand why. When people go to a joint school and they learn, they're in a nice environment, they've got a nice flat floor, they're in an air-conditioned building, they can walk all the way around the cable, it's easy. When they're doing this in the field, it could be in 50-degree heat, it could be in -20-degree heat, it could be raining, humid, in a muddy hole in the road somewhere. It could be Friday afternoon and they want to go home. These things lead to people, making mistakes. Jointers don't set out to make mistakes. They make mistakes because they're either rushing or the conditions aren't conducive to making a good joint, or they've been poorly trained. And poor training is definitely a problem in some parts of the world. So another two questions related to PD. So partial discharge, usually once the cable's in service, normally PD testing is done from the ends of the circuit, from the terminations, particularly for medium voltage cables. And you can see probably up to about 4 kilometers down the cable and still detect partial discharge up to 4 kilometers away. So for medium voltage cables, generally testing at either end of the circuit, you will see those discharges all the way along the route. High voltage, extra high voltage circuits, tend to be longer. You have bigger joints, and so you can potentially do PD testing at the individual joint locations, either as a spot test if you have access to the cables, or people for EHV cables will often put permanent PD monitoring in these days. So in principle, we can perform PD testing on any type of cable. It tends to be applied more frequently to solid dielectric cables, EPR, XLPE, less so to oil-filled cables, because to get PD, we need some form of void. And if you have an oil-filled cable, the oil naturally tends to flow back in and fill up a void. However, there are instances in things like oil-filled sealing ends where if there's a leak, either out of the sealing end or on occasions under the sheath of the cable, and the oil level in the termination drops, then you'll pick up PD inside the termination because the oil isn't there anymore. How can the cable be prevented from failing? Well, that's hard, because in some instances, I had a case a few years ago where we thought that there was a design issue with the cable and it was going to fail in quite an unusual manner. And we proposed putting some permanent monitoring in to test the hypothesis as to how it was failing. Again, we made the recommendation earlier this year. I had an email from that company going, we found your name on a report from 5 years ago. We've just had another failure. To which my question was, well, did you put the monitoring in to check? And the answer was no. It's like, well, okay, so we're 5 years on, you haven't learned anything. I predicted they would have more failures. Okay, it took 5 years for another one in this particular case. But to be able to predict failures or prevent them, you have to kind of know what the failure mechanism is. So if we have medium voltage cable that could fail through water treeing, VLF hand delta is a really good tool. If you're not going to fail through water treeing, Usually in its polymeric, periodic PD testing, is probably the best approach, along with routine maintenance to make sure things like the earthing systems are fine. You don't have excessive circulating currents. You don't have sheath damage, etc. So it's your periodic maintenance, maybe supplemented with something like partial discharge. That must be follow on to somebody else's question. So somebody's asking about white deposits on the insulation shrink tubes. That's quite specific. That's probably poor installation and the placement of support bars in the terminations. So Robert, I will follow up with you on that afterwards because that's very niche and specific. So somebody's asking about, are old cables more likely to fail? I would probably suspect that old cables are probably less likely to fail. As I say, most of the problems these days are jointer error related. That's not to say they all are. I've got another case recently where, again, I think it's a cable design issue. But most of the problems seem to be around installation problems. So generally, if you have an installation problem, it will fail fairly soon after installation. Once it gets past a few weeks and it hasn't failed, there's a good chance it'll still be working 25, 30 years later, unless the cable gets damaged. Somebody's asked, did the splice installation instruction identify the required outside diameter of the connector? The answer to that is I don't know, because I never got any information on the type of joint. I could work out what the type of joint was. But normally the splice kits, come with all the requisite parts. So I wonder whether in this particular case study I was talking about, whether the contractor tried to save money by buying all the various bits separately, and had caused the problem in that way. I normally, as I say, you would buy a joint for a particular size cable with a particular size conductor and that conductor connector. And of course, these days it's far more common to have shear bolts than it would be to compress the conductor together. And the shear bolt ones it's easier to have a bigger connector in those cases because you're not trying to crimp a much bigger diameter piece of metal. Wow. Does thumping potentially cause other damage? Yes and no. You're not normally thumping the cable with a particularly big voltage, but it depends what type of damage you might expect to have in the cable. So if you have water trees, then in a medium voltage cable, water trees are more likely to convert to electrical trees if they see voltage transients like thumping. That said, there was a utility in the US some years ago, had a very wide geographic area, and they used to deliberately go out and overstress their cables with VLF testing as a way of killing off the weak cables. So they would go to a higher voltage than the IEEE document 400 document would recommend, the crew would be in the area for a week or two, and then if they had subsequent failures, they were in the area, they had the spare parts with them, they would go and do the repair. So that was kind of culling the weakest in the population. Somebody's asked, will you get an attendance certificate? Unfortunately not. Given the number of people who listen into these webinars, it would be a huge problem for us. I apologize for that. They've left. What would I consider to be excessive circulating current? That's going to be in excess of what it's designed for. So again, depending on the voltage level of the cable, is going to you're going to have all sorts of different earthing arrangements, whether that's single point, double point, cross bonded, and so there will be an expected circulating current for a particular earthing arrangement. But if you want to follow, I've left your email address, so I will send you an email later. The person asked that question. And we have one final question, after which I will stop unless anything else comes in the next 30 seconds. You mentioned maintenance to prevent failures. What kind of maintenance? The person who's asked that, there are some very good C-grade documents on cable maintenance. And sorry, I thought I might have actually had it next to me. I was going to give you the number. But if you search the C-grade website, or I can send you an email later, there are a couple of good brochures. There's one that came out just a year or two ago, which talks about the different types of cables, what you might want to do to them, the pros and cons of different methodologies, maintenance methods. And also, there's also some, because C-grade did a big survey at the time, there's some statistics in there as well on who's doing what. So what percentages of utilities who responded to the survey are doing, say, sheath testing or insulation resistance testing or VLF testing. So it kind of gives you a good idea of what's popular and what people think is effective. And there are some other techniques that only one or two people do, but they clearly do them because they think there is value in them, or that they've had some particular failure in the past that this technique can detect, and so they're, I won't say paranoid, but they're sensitive to that particular failure mechanism, and so they still do that methodology. So if there are no other questions, I will wrap up. I will get a list of everybody who's asked a question and your email addresses. So I will drop people an email. My email's on the screen there, so if anybody wants to send me a message, please feel free to do so. More than happy to help answer questions. And thank you very much for attending. Please take the time to fill in the survey. Sorry, somebody else wants some more information. Please take a few minutes to fill in the survey. We really appreciate it. It does help us, make better webinars and actually address the things you kind of want to hear about. So thank you very much, and we look forward to seeing you on a webinar in the new year. Enjoy the rest of your day. Bye-bye.